In late 2024, the LIGO-Virgo-KAGRA network detected two black hole collisions just a month apart. These events, designated GW241011 and GW241110, challenged our understanding of how these objects rotate. In the November event, the primary black hole was spinning in the exact opposite direction of its orbital path. The October event was equally strange, rotating so fast it pushed the absolute physical limits of spinning without breaking apart. In existing models, isolated black holes born from single collapsing stars do not behave this way. They should spin in the same direction they orbit, and they rarely reach such velocities on their own. To explain these erratic spins, scientists realized they were looking at second-generation black holes, objects formed not from a single dead star, but from earlier black hole collisions. This chain reaction requires a specific environment. Deep in space, there are incredibly dense star clusters, where objects are packed so tightly that black holes constantly cross paths, crashing and emerging over and over again. The data supports this history. In both of the late 2024 events, the larger black hole was roughly double the mass of its partner. That size imbalance is a physical signature of a hierarchical merger, where one object has already consumed a previous partner. Because these survivors have absorbed the rotational energy of multiple past collisions, they spin so fast they warp spacetime into a natural laboratory for testing the boundaries of physics. When an object rotating at these velocities, immense centrifugal forces stretch and deform its shape, pulling the spherical event horizon into a flattened, oblate state. This deformation is observable. This diagram shows gravitational wave frequencies. Notice that alongside the primary wave created by the merger, there is a smaller, distinct harmonic overtone, a faint hum hiding within the signal. During the October collision, observatories captured this specific overtone with superb clarity. The frequencies aligned with the mathematical solutions for rotating black holes, developed by mathematician Roy Kerr. By confirming Kerr's math, this signal also served as a rigorous stress test for Albert Einstein's predictions, verifying his work under some of the most intense gravitational strain ever observed. These rotational fingerprints prove our foundational equations of gravity hold true, even in the most violent environments in the universe. These massive spinning objects also provide data for particle physics. Researchers use them to search for ultralight bosons, theoretical elementary particles that exist outside the current standard model. If these bosons exist, they would interact with rotating black holes. Over time, a particle cloud would accumulate, creating a drag effect that gradually saps rotational energy and slows the spin. Yet the October black hole maintained rapid rotation for millions of years. If these bosons existed, rotation would have stalled. The persistence of this spin allows physicists to confidently cross entire categories of theoretical particle masses off their list, narrowing the hunt for new fundamental particles. To understand the value of this rotation, we have to address a puzzle that currently separates gravity from quantum mechanics, the black hole information paradox. According to general relativity, Stephen Hawking discovered that black holes slowly leak thermal energy and eventually evaporate away to nothing, seemingly taking all the physical information of whatever fell inside them out of existence. But in quantum mechanics, there is a rule. Physical information can be scrambled or change form, but it can never be permanently deleted from the universe. Resolving this contradiction requires a different understanding of a black hole's internal structure, one that emerges only through rotation. This diagram of a rotating Kerr black hole reveals a hidden inner horizon. Under a new quantum wormhole model, particles falling past the outer shell aren't trapped in a singularity. Instead, they are absorbed at this inner boundary and re-emitted, preventing information from being lost. This internal absorption and emission mechanism mathematically functions like quantum teleportation. The particle's quantum state is destroyed at point A and precisely reconstructed at point B across a quantum channel. By detecting these massive second-generation spinning black holes, we are gathering the evidence needed to finally bridge the gap between cosmic gravity and the quantum realm.